Imagine for a moment that every piece of metal you see today was as expensive and as difficult to produce as high-end jewelry. Think about the skyscrapers that define our modern cities, the massive bridges spanning wide and turbulent rivers, and the thousands of miles of railroad tracks that connect the corners of the world. In the early 1800s, the material needed to build those things existed in theory, but it was a rare and precious luxury. Steel was the dream material of every engineer because it was strong, flexible, and durable. Yet it was so incredibly hard to make that it was mostly reserved for the most delicate or specialized of items, such as sword blades, watch springs, and fine surgical tools. If you wanted to build a bridge out of it in those days, you might as well have tried to build a bridge out of solid silver. The world was effectively stuck using iron, and iron had some very dangerous and frustrating limits that held back the progress of humanity. Before the middle of the 19th century, the industrial world ran primarily on two types of iron, neither of which was perfect for the demands of a growing society. On one hand, you had cast iron. It was relatively easy to melt and pour into molds, which made it a great choice for things like heavy cookpots, stove parts, or the sturdy frames of early factory machines. But cast iron had a fatal flaw. It was incredibly brittle. Because it contained a high amount of carbon, it lacked internal flexibility. If you hit it too hard or put too much unexpected weight on it, it would not bend or dent, it would simply shatter like a piece of glass. This made it a terrifying material to use for things like railroad bridges, where the vibration of a passing train could cause a catastrophic failure in an instant. On the other hand, you had wrought iron. This was a much tougher material that could take a beating without snapping. It was fibrous and resilient, but it was also quite soft. It would bend and deform under heavy loads, losing its shape over time. More importantly, making wrought iron was a back-breaking, agonizingly slow process. It involved skilled workers literally stirring molten metal in a hot furnace with long rods to manually burn out the impurities. This was known as puddling, and it was artisanal work performed on an industrial scale. It was exhausting, dangerous, and simply could not keep up with the hunger of a world that was beginning to move faster and build bigger. The bottleneck of the entire industrial age was the chemistry of carbon. Iron becomes steel when it has just the right amount of carbon in it, not too much and not too little. But in the mid-1800s, getting that balance right was like trying to cook a perfect soufflé in the middle of a massive bonfire. You either had the brittle, high-carbon cast iron or the soft, low-carbon wrought iron. To get steel, you usually had to take wrought iron and then painstakingly add carbon back into it through a long, expensive process that took days or even weeks. This was the hard constraint that stopped the Industrial Revolution from truly taking off into the stratosphere. We had the steam engines, and we had the ambitious designs for massive structures, but we lacked the literal bones required to build them. The world was waiting for a miracle of chemistry that could turn common iron into the strong, flexible backbone of a new era. The turning point came from a realization that sounded completely insane to anyone who understood the basic nature of fire and heat. At the time, a few bold inventors began experimenting with the idea of blowing cold air directly into a vat of molten iron. To a traditional blacksmith who had spent his life protecting his metal from the air, this sounded like a recipe for immediate disaster. Common sense tells you that if you blow cold air on something hot, it cools down. However, a few curious minds realized that the impurities inside the iron, specifically the carbon and the silicon, were actually potential fuels. If you shot enough oxygen into the liquid metal, those impurities would start to burn. Instead of cooling the metal down, this chemical reaction would generate an incredible amount of heat. The metal would literally cook itself from the inside out, using its own impurities as the wood for the fire. The reaction was so violent and so efficient that it could burn away the excess carbon in a matter of minutes. When this was first demonstrated, it was a terrifying and awe-inspiring spectacle. Imagine a massive, pear-shaped iron vessel, tilted on its side. filled with several tons of glowing orange liquid metal. As the air began to roar through the bottom of the vessel, a fountain of brilliant sparks and a pillar of roaring fire would shoot out of the top, lighting up the sky for miles around. It looked as though a volcano had been captured and put to work in the service of man. In about 20 minutes, what had started as crude, impure iron was transformed into a massive, shimmering pool of glowing steel. This was the scaling trick that changed everything for our species. A process that used to take weeks and required a small army of exhausted, highly skilled laborers was suddenly replaced by a machine that could produce more steel in one afternoon than an old-fashioned refinery could produce in an entire year. However, the road to global success was not a straight line, and the initial excitement was followed by a period of deep doubt. The early batches of this new steel were often terrible and unpredictable. Sometimes the metal was still too brittle to use, and other times it was full of tiny air bubbles that made it weak. The inventors eventually realized that they had a hidden phosphorus problem. If the iron ore used in the process had even a tiny, microscopic amount of phosphorus in it, the resulting steel would be ruined. It took years of tinkering and the help of other brilliant chemical minds to realize that adding a specific blend of minerals and a final dose of a carbon-rich alloy at the very end of the blow would fix the chemistry. Once they figured out how to standardize the output and handle different types of ore, the floodgates of industry truly opened. Steel was no longer a luxury reserved for the wealthy or the military. It was becoming a common commodity, and its price began to fall as fast as its production rose. As the price of steel plummeted, the physical world began to transform at a dizzying pace that no one had seen before. The most immediate and visible change was on the railroads. Before this breakthrough, train tracks were made of wrought iron, and they were a constant, expensive nightmare to maintain. On busy routes, those iron rails would wear out, bend, or snap in just a few months under the weight of the locomotives. When steel rails became affordable, they lasted 10 or 20 times longer than iron. This meant that trains could be made significantly heavier and faster, and they could carry much more cargo across vast distances. The cost of moving food and goods across entire continents dropped sharply, which fundamentally changed the way the global economy functioned. Suddenly, a farmer living in the middle of a vast continent could sell their grain to someone living thousands of miles away across an ocean because the steel rails made the transport cheap enough to be profitable. But the transformation was not just limited to the rails on the ground. Cheap steel changed the very shape of our civilization and the way we occupied space. Architects and engineers realized that if they used steel beams for the internal skeletons of buildings, they no longer needed thick, heavy stone walls to hold everything up. In the past, if you wanted a tall building, the bottom walls had to be so thick that there was hardly any room left for people. Steel changed that math. Buildings could now go higher than anyone had ever imagined possible. The skyscraper was born directly from this abundance of cheap, strong metal, allowing cities to grow vertically and house millions of people in small geographic areas. At the same time, shipbuilders moved away from wood and iron to create massive steel-hulled vessels. These ships were lighter, stronger, and much larger than anything that had come before, allowing for the birth of global trade as we know it today. They could withstand the punishing waves of the deep ocean while carrying thousands of tons of goods. The scale of human ambition was finally matched by the strength of the materials we had at our disposal. This shift created winners and losers on a massive scale. Cities that were located close to iron ore and coal deposits exploded into industrial giants, while older manufacturing hubs that could not or would not adapt fell behind and faded. The new era required a level of organization and systemic thinking that had never existed before. You could not just have one guy making a bit of steel in a backyard furnace anymore. To make this work, you needed massive factories, complex supply chains, and thousands of workers operating in perfect, disciplined sync. This led to the birth of the modern industrial corporation. Quality control became a rigorous science, because when you are producing thousands of tons of metal, a single mistake in the chemistry could lead to a catastrophic bridge collapse or a train derailment. Standards had to be created, and for the first time in history, an engineer in one country could order a specific grade of steel from a factory in another country and know exactly how much weight it could hold without even seeing it. Why does this story still matter to us in a world dominated by computers and the internet? We often think we live in an age of purely digital infrastructure, but that digital world still sits on a physical foundation made of steel. Every data center housing our information, every power plant generating our electricity, and every shipping container moving our products is a direct descendant of that first volcanic blast of air into a liquid iron converter. The leap from artisanal steel to industrial steel was the first time humanity figured out how to take a complex chemical process and scale it to a level that could support billions of people. It set the pattern for how we think about technology even now. We look for the bottleneck, we find the counterintuitive insight to break it, and then we build a massive system to repeat that success until the luxury becomes a common utility. We often talk about the great inventors as if they worked in a vacuum, but the story of cheap steel shows that technology is a team sport. It took the original insight of one person, the chemical corrections of another, and the massive financial risks taken by business leaders to turn a laboratory experiment into the backbone of the modern world. It reminds us that progress is not just about the big idea, but about the grueling, repetitive work of making that idea reliable, cheap, and universal. When we look at the skyline of a modern city, we are not just looking at glass and light. We are looking at the frozen energy of that 19th century breakthrough. Now we see how steel gave us the raw material to build big, but building big is only half the battle when you need every piece to fit perfectly. We are going to take a quick step sideways in our story to look at the missing context of interchangeable parts and precision machining. This leap in how we measure and manufacture is what truly unlocked the potential of all that new steel. If you want to see how the modern world became a puzzle of perfectly fitting pieces, subscribe and join us for the next chapter.